In this next module, I'm going to talk about the statistics that are used to describe where's the center of your data. So the main measures that we use for central tendency, that is where's the center of your data, are the mean and the median. Probably most of you are very familiar with the mean. So a mean is just an average, and you've probably all calculated averages throughout your life, so this is not something that's very hard, but I want you to think a little bit about the mean in a different way. I want you to also think about the mean as a balancing point. I'm going to show you that in a minute. I also want to show you the mathematical shorthand, the mathematical symbols that we use to represent the calculation of a mean. I'll be using some of these symbols in this class, so it's helpful for you to be comfortable with these. So how do we calculate a mean? It's very easy. We add up all of the values and we divide by the sample size. Again, probably many of you have calculated many of these in your life. But how does that look in math shorthand? So in math shorthand, the way that I'm going to represent a mean is I'm going to write X bar. And that's important to remember because I'll be using the X bar a lot just to save myself the time of having to write out the word mean. So it's a little bit of math shorthand that I will be using in this class. So X bar represents the sample mean. When I take some data and I calculate an average or a mean, that I will represent as an X bar. The way we calculate X bar, the mean, is to add up all of the observations and divide by n, and that's represented by these symbols here. So here's my summation sign. So what this summation sign is saying is add up all of the observations from 1 to n, because again I have n observations in my sample. I'm representing each observation as xi, so that x1 would be the first observation, x2 is the second, etc. And this just says add up all of those observations. And then we divide by n the total number of observations, and this is a longer, over here is a longer way to write that. If these symbols are a little unfamiliar to you, like if you haven't seen a summation sign before, you should take the math tutorial that's offered before you take the rest of this course, because I will be throwing up some summation signs every now and then. So let me just give a quick example of how to calculate a mean. This should be easy for all of you. So for example, let's say I had some hypothetical data here. I have some data on 8 participants in a study, and I have their data, their ages. So it ranged from 17 to 38. If I wanted to figure out their average age, I would just add up those 8 values and divide by 8. When I do that, I come out with a value of 23.25. So again, I think that should be pretty easy and familiar to most of you. Now I'm going to show you some of the example data on my Stanford students. So for example, I asked them to report how many hours a week they spent on homework. And you can see the distribution of homework, the homework variable here in a histogram. Well, it turns out that the mean for homework in my student sample was 11.4 hours per week. So on average, students were doing about 11 hours of homework. Now, as I mentioned, you can think of the mean as a balancing point. So imagine, this kind of harkens back to high school physics a little bit. Imagine that, that this graphic that you're seeing here, this histogram, is actually a lever, and each of these little red bars represents a mass. So the smallest red bar is a small mass, the biggest red bar is a big mass. So just picture this as being sort of a lever with masses on it, and here is the balance point. Here's the fulcrum, and the goal here is to balance this like a seesaw, to balance it so it's perfectly balanced. The mean is the point at which if you put where you put the fulcrum, that you will balance these masses. And if you remember back to basic physics, if you've ever done anything with levers and fulcrums, you will remember that there was a principle that said the further away a mass is from the fulcrum, the more force it exerts, right? So there was a formula that said that force was equal to mass times distance. So the mass matters, but also how far away from the center you are matters. And so there's the same principle applies with means. The farther something is away from the mean, the more influence, the more pull it has on the mean. So let me illustrate that now. So take, for example, the variable alcoholic drinks. So here's the histogram for alcoholic drinks. I asked students to report how many drinks they had in drinks per week. And I'm showing you the histogram here. For my student sample, the mean was 2.3 drinks per week. It's pretty low, and again, you can think of that as the balancing point. So I'm going to have to put the fulcrum at 2.3 in order to balance this lever that has masses stacked on it. And if you were to take the very highest value and change that and make it higher, that will have a big effect on the balancing point. So again, the further you are from the balancing point, the more force you're having. So for example, what if I were to take the person who drank the most, which was only 8 drinks per week, and I was to make that a much higher value, like pretend that that person actually was an alcoholic. So imagine that the highest value was no longer 8 drinks per week, but it was all the way up at like 40 drinks per week. So I had an alcoholic in the data set. If I were to pull that one value, which has very little mass, remember it's only 1 out of 50 people, so it's a very small mass. If I were to pull that one value really far from the mean, in order to balance this lever now, so again, imagine that this is just like a long board here. You've got masses on it. In order to balance this, this is having a lot of force now because it's so far. So to balance this, I'm actually going to have to pull the fulcrum quite a bit to the right in order to balance this lever now. So that one little mass, it's a very tiny amount of mass, because it's so far from the mean, it has a huge influence on the mean. So the mean, if I plot my new data in histogram where the highest value is 40 rather than 8, that pulls the mean all the way from 2.3 drinks per week up to 2.9, almost 3 drinks per week. So one person going up to 40 has a huge influence on the mean. This is only one person out of 50, but it's having a big influence on the mean. Now I want to take a moment here and tell you a little bit about, I mentioned binary variables in an earlier module this week. Binary variables have only 2 categories to them. It might seem odd for me to tell you that a binary variable can have a mean, but in fact, a binary variable can have a mean if you code that binary variable as a 0-1 variable. And it turns out to be useful for a lot of situations in statistics to think about binary variables as a series of zeros and ones and to kind of think of them numerically so that you can treat them numerically. You can calculate things like averages. So for example, if you take in my example data set, I had asked the students whether or not they played varsity sports in high school. That's a binary variable, a yes-no variable. If I code that in my data set, rather than coding it as no and yes, if I code that as 0 for no and 1 for yes, and I actually think about those zeros and ones as numbers, I can in fact calculate an average for this binary variable. So again, here's the histogram for played varsity sports in high school. 30 or 60% of my sample had played varsity sports, 40% had not. What if you thought of that as a series of zeros and ones? How would you calculate the average? So let's do that. How would I calculate the average here? Well, I've got 20 people who have a value of 0, 30 people who have a value of 1. So I'm just literally going to add up those 30 ones and those 20 zeros, which just gives me a value of 30. And I'm going to divide by the total number, which in this case is 50. So 30 divided by 50 gives me a value of 0.6. So notice that the average here is just the percentage of people who answered yes, the percentage of those who played varsity sports in high school. But you can calculate an average. It comes out to be 60%, 0.6 in this case. The other way that we tend to measure central tendency, other than the mean, is something called the median. The median is the exact middle value. So that means if you were to rank everybody's from the lowest value to the highest value on whatever variable you're considering, it would be the value that fell right smack in the middle. Now, if there are an odd number of observations, like there's 101 observations, then there will be one value right in the middle. But actually, if you have an even number of observations, then there's going to be 2 values that are smack in the middle. So what we do in that case is we take those 2 values and we just average them. We add them up and divide by 2. So let me give you an example of how we calculate the median. So from this hypothetical data set on the ages of participants, in order to calculate the median, I have to line up the ages from the lowest, 17, to the highest, 38, which I've done here. And then I have an even number of observations, so I'm going to have 2 middle values. So I'm going to take those 2 middle values, 22 and 23, and I'm going to average them, just add them up and divide by 2. So my median occurs at 22.5. That means half of my observations are below 22.5, and half are above 22.5. So if 22.5 is here, 4 observations are below, 4 are above. Half are below, half are above. That's the median. So for example, what if I ask, what's the median of homework? So it turns out that the median of homework in my data set was 10 hours per week. So that means half of my students were doing less than 10 hours per week, and half of my students were doing more than 10 hours per week. If you think of this again as masses, those bars as masses, that means 50% of the mass is below 10 and 50% of the mass is above 10. For alcohol drinking, the median turned out to be 2.0 drinks per week. So half of my students had less than 2 drinks per week, half had more than 2 drinks per week. And unlike the mean, the median is not affected by extreme values. So because we're just talking about where 50% are above and below, it doesn't matter if there are extreme values in there. It doesn't matter if in the top 50% somebody has a really high level of drinking or whether the highest value of drinking isn't so high. So for example, if I took the highest drinking person, which was only 8 drinks per week, and again I made them an alcoholic, I said that the highest drinker actually had 40 drinks per week. How does that affect the median? Well, it doesn't affect the median, right? Because 50% of people are still below 2 and 50% of people are still above 2. It doesn't matter that the highest person doesn't matter whether they're at 8 or whether they're at 40. That doesn't affect where the median lies. So the median is not affected by extreme values. Now, I asked whether or not varsity sports has a mean. That's a binary variable. Does varsity sports, a binary variable, also have a median? Sure, again, if you think about a binary variable as a series of zeros and ones, then you just line up the zeros and ones from the lowest, the zeros, to the highest, the ones, and you find where the middle number lies. Well, in this case, there are more ones than there are zeros because more people had played varsity sports than hadn't, so the middle number, the median, will occur at 1. So yes, it has a median. It has a median of 1.